and share my screen. Okay. Let me make this a little bigger. Okay. Let's see. I think the only other thing I want to say is good job, everybody who's continuing to keep up with their assignments and everything in Canvas. I feel like everybody's been really on top of that, but just want to reiterate to you, if you ever realize, oh shoot, I missed something, you can always do it ahead, a little bit late. That's not a big deal. We really want everybody to finish everything by the end of the sprint. That makes everybody's life helpful, because if anybody has outstanding assignments, a lot of them at least, either Ryan or I have to come track you down, and that's not so fun for anybody. So yeah, just, make sure to take a minute to do that. If it's, not the night before, then during the warm-up period. And the other thing that I was going to say was, oh yeah, if you ever have any issues with the module projects, we're still trying to make sure that we get all the settings correct. As far as like, not locking people out if they pass a deadline or something like that. But I think Monday I may have had the setting not right, and it's different between CodeGrade and Canvas, whatever. Anyway, so if you ever get locked out, let me know and I will let you back in, because that's not really intentional. Okay, so assignment stuff, I think that's out of the way. Of course, ask any questions if you have any. But so today we are going to talk about what's called confidence intervals. So this is basically the other half of the hypothesis test piece. So, we've got what are confidence intervals, why make them? Well, so up to this point with t-tests and chi-square tests, we've said, we can reject the null hypothesis, include the alternative hypothesis is true, but that's actually not like hugely informative, because it's sort of like, okay, if I reject the null hypothesis and I say the normal human body temperature is not 98.6 degrees, well, of course, the following one question is like, well, okay, what is it? Or, if the caffeine content in the fountain soda is not 34 milligrams, well, what is it? So today we're at the point where we answer the question like, okay, what is it? If it's not that, then what is it? So we are going to focus on doing hypothesis tests for a single population mean. So this is going to be sort of the analogous procedure, or this is like the counterpoint to the t-test, basically. So there is a way to do something similar with a chi-square test, but it would be a confidence interval for what's called an odds ratio. And so that's a measure of the likelihood of something happening compared to it not happening. It's a little bit specialized. So we're not going to spend a lot of time on that. And once you get the sense of, okay, this is what it is for the t-test, if you ever have to make another confidence interval, it's going to work the same way. You're going to get the function that says, whatever interval, plug stuff in, and the interpretation of the confidence interval you get out at the end is going to be the same. So the purpose of a one sample, it's a confidence interval. I actually don't really like that statement. The purpose of a confidence interval for let's say the purpose of a confidence interval is to estimate a population parameter. In today's guided project, we will calculate a confidence interval for a population mean. So we don't know the mean of the population. We want to make a guess about it, and we will do that using a confidence interval. So the nice thing about confidence intervals is that unlike hypothesis tests, they are pretty intuitive. So we already make informal confidence intervals all the time. So confidence interval is basically like we're going to guess and we're going to guess a range. And what makes it special and statistical and mathematical is that we're going to use math and the t-distribution to come up with that guess, come up with that range of possible values. But at the end of the day, it's an educated guess. And we're pretty good at making educated guesses with ranges. That's, again, it's a pretty natural thing. So for example, somebody asks me, how long will it take the batch of brownies to bake? Well, I'm probably not going to guess. I'm not going to say, oh, I think it's going to be 34.576 minutes. I'm going to say, it's going to be like 35, 40 minutes. Or, how many cookies should I bake? Well, 2 or 3 dozen. And so in those cases, when I'm making an informal confidence interval, I'm using information and experience that I have, or maybe a recipe or something like that. Like I'm using external information to make my educated guess. And so similarly, we're going to use external information, both from our sample, sorry, my eyes itch, and from the t-distribution to make our educated guess about the population parameter. For as cold and snowy as it is for every place else, here it's hot and we have pollen like crazy in Florida. It's like, oh my gosh, my allergies are going nuts. I wish we could just all take our weather and merge it and mix it all together so it was nice everywhere and not so awful everywhere. Okay, so let's talk about the anatomy of a confidence interval, all the pieces and parts. Here comes the math part. This is the mathiest thing, I think. It's certainly the mathiest thing that we will do for you, Sprint 2. Sprint 3 might have one day that's a little bit more mathy, but anyway. So, and this is like arithmetic mathy, so don't get anxious. All right, so when, sorry, I kind of already said this, but when we make brownies, so we make an informal confidence interval about how long it will take them to bake based on the recipe and our baking knowledge, et cetera, how Mary Berry likes her brownies. But when we make a confidence interval from a population mean, our ingredients, if you will, our recipe, I guess I should say, is going to come from information from our sample and mathematical properties of the t-distribution. So we've got a formula, one of the few formulas that we're going to use, but in this case, I do think looking at the formula for a confidence interval and actually like analyzing the parts does help understand, or help one understand what a confidence interval is and where it comes from. This is not always true for some things, but I do think it's true in this case. So the first thing we've got is we've got X bar, and that is a symbol that we use to represent the sample mean. Because if we think about it, right, we've got a whole population. We took the time to go on and get a sample from that population. And we want to estimate the population mean. Well, what does it make sense to estimate the population mean using? Like, what is the quantity that we can actually get our hands on that's probably closest to the thing we want to estimate? Well, the sample mean, right? We expect, again, by the central limit theorem, that our sample mean ought to be pretty darn close to the population mean. So we are going to estimate our population mean starting out by looking at our sample mean. Seems reasonable. So the other pieces that we're going to need from our sample, so we've got our sample, that's our data set is our sample. So we calculate the sample mean. We also need to calculate S, which is the sample standard deviation. So we can get this, this is displayed when we do .describe, and you can also calculate it using the .std function. And then the last thing that we're going to need from the sample, so this is actually 3 out of the 4 pieces that we need to calculate this thing, is the sample size. And again, 1, 2, 3 out of these 4 quantities are things we're going to calculate directly from the sample. So one thing we want to notice here too is this quantity, S over the square root of N, is called the standard error. And we actually saw the standard error come up when we were talking about the central limit theorem, because we said that that whole quantity, the standard error, is, is the thing that tells us how close our sampling distribution of our sample mean is from the population mean, or how spread out it is. So thinking about the rolling the dice thing, right? It's like when we were doing the simulator and we were rolling the dice and we were only rolling 1 or 2 dice at a time, all of those means were pretty spread out. And when we were rolling 20 dice at a time or 30 dice at a time, our bell curve was squished into the middle. That quantity, the standard deviation over the square root of the sample size, tells us how spread out or squished in our distribution is. And the one thing that we remember is here, I'm going to click out of this so you can see the actual notation, is we call it the pizza rule. So the pizza rule is if you have a fraction and you make the denominator bigger, it makes the whole quantity smaller. Because if you've got 1 over 2 slices of pizza, so a half of a pizza is bigger than 1 over 3, a third of a slice of pizza is bigger than 1 over 4, is bigger than a fourth of a slice of pizza. And as we slice the pizza up into more and more and more pieces, 1 over that number of slices is a smaller amount. So as we make the denominator of this fraction bigger, so as the sample size gets bigger, the variability gets smaller. The whole quantity, the variability gets smaller. The standard error gets smaller. So if you want to tattoo something on your arm to go along with this, and the other things are hypothesis test tattoos that you could get, is bigger sample size is always better. I mean, this is really kind of like getting in the weeds a little bit to explain how it all works. But at the end of the day, if you ever have any question about to do a sample size, think about whatever the good thing is that you would like to have happen, and bigger sample size always goes along with whatever that good thing is. So in this case, bigger sample size is going to mean a smaller margin of error. We're going to have our squished in towards the population mean. Okay, so we talked about the sample mean, we talked about the standard error. We've got this thing called T-star that we're not going to talk about yet. That's our last piece. That's the thing that's going to come from the T distribution. But another reason that I want to point out this formula is because this whole quantity, this T star times S over the square root of N, so T star times the standard error, has a special name that you have probably heard used before, and that is the margin of error. So when you, this was great back when we all used to go to hotels and we would get USA Today's slid under our hotel room door. But often in USA Today, I ought to even just see. This may fail completely because I haven't actually tried to do this. But they would always have an infographic on the very front page, and it would always say something like, well, I guess they don't. Okay, I thought I'd try it, but it would always say something like, 86% of Americans love cats, little asterisk, and at the bottom would say little asterisk plus or minus 2%. So you see this all the time. We just went through the whole election thing. You see this all the time in election polling. It'll say, 50% of Americans support, I don't know, free pizza delivery, plus or minus 5%. And so that plus or minus 5% or 2% or whatever that you see in those articles, that's the margin of error And that amount is actually the amount that you would add or subtract from that number that was quoted in the article. So 86% of Americans love cats, plus or minus 2%. If you add and subtract that 2%, that's actually going to give you, that's actually a confidence interval that they're creating there. So I just want to point that out to you, that actually a lot of times in print, in news articles or whatever, we do see confidence intervals reported. We just see it reported as, sample mean or proportion, and then later on, little star, later on, plus and minus whatever percent. So that's a word worth sort of just being able to kind of know in the back of your mind. If you read and you say margin of error, you're like, oh, okay, that's sort of like we're making a confidence interval. Okay, so we talked about the margin of error. And so nearly all the information we said that we need to create a confidence interval comes directly from our samples. So we got the sample mean, the sample standard deviation, the sample size. We just have this thing that we're going to need from our t-distribution called t-star. And we're going to put off talking about that because that's the hard part. But we'll get there. So what we're going to do, though, is we're going to start by just looking at and reminding ourselves, what all these other quantities are, how do we get them from our data, and start to plug everything in. And I think as we plug stuff in, it's going to become more intuitive what this whole t-star thing does. All right, so we're bringing back the temperature data set. We can just run our data here. So again, we've got some body temperatures. And so before, on Monday, we rejected the null hypothesis that, oops, sorry, I'm looking at something here real quick. We rejected the null hypothesis that we were going to, that the normal human body temperature was 98.6 degrees, and we concluded that it was not 98.6 degrees. So then, of course, the question becomes, well, like, what is it? So this is the point where we decide, okay, what is it? I mean, it's probably not, the mean healthy human body temperature in the entire world is probably not exactly equal to the mean temperature we found in our sample, but it's probably pretty close. So rather than saying, well, we guess it's exactly equal to what's in our sample, again, we're going to make this confidence interval, and we are going to propose a range of values for what we think the normal human body temperature is. So Andrew asks, so then using that information, wouldn't you yes, this is a good question. Yes. Okay. So Andrew says, one thing you might want to be able to do, I'm rewording your question based on what I think that you're asking, is, okay, so the question is like, could you go the other way around? Could you say, okay, I would like to fix my confidence interval. Like I would like to be able to say within whatever margin of error, like within 1% or something like that, what I think the true population mean or proportion is. Can I go backwards and find the sample size that I need to do that? And the answer is yes. Yes, you can do that. And that's often a really important thing that people will do, especially like if you are trying to prove that you can, let's say, estimate something within, have a confidence interval that's only got a certain amount of margin of error. You might want to, or have to, be able to show that your sample size is big enough to have a confidence interval that small. Or yeah, you might want to say, well, I need this result to this precision. What sample size do I need to get for that? So yes, that's definitely an important thing. All right, so hopefully that answered your question, Andrew. Okay, so we need to get the sample mean. And who remembers, because it's been a little while, who remembers what function that we need? Oops, I'm in the wrong spot. What function we need to use to calculate the mean of a set of numbers from a pandas data frame? Very good. Mean. So I'm gonna assign all these quantities to actual variable names because I'm gonna want to be able to make use of them later. So I'll say mean body temp is equal to, I guess I called this data frame the DF this time. DF body temp dot mean. So I can run this, and my mean body temperature is about 98.2 degrees. We said, you know, normal human body temperature exists in such a like small range, basically, that just being this much below 98.6 degrees is, you know, a significant difference. We believe that, you know, this sample mean of 98.2 degrees gives, you know, enough evidence that we don't really think that the true population mean is actually 98.6 degrees. So we also need to calculate the standard deviation. So what function do I need for the standard deviation? Yep, .std, very good. Oops, temp. Right, so the standard deviation of body temperature is about 1/2 of a degree. So that means that most individuals, so remember, if we're talking about the distribution of individual body temperatures, most individuals will have a body temperature within plus and minus about 3 standard deviations of the mean. So we would expect most individuals to have a body temperature somewhere between, let's say, you know, 96.5, to 90, you know, 9.5 degrees. We're going to be talking about the mean body temperature, the mean of a group of people, so not individual body temperatures. That's why we're going to divide by the square root of n, because we're going to be looking at the variability of the sample mean, not of individual body temperatures. So if I want to figure out how many observations that I have, what function could I use to do that? There's a couple ways that I can think of. Yep, shape. I could use shape and select just the first element. I could use describe and get that out. And I can use length. So just for now, I'm going to use length. And I'm going to use length of my whole data frame. But you could also get this information out of shape or describe. And so I've got 233 individuals. And just to check, if I do print the shape, I do see I have 223 rows. So that gives me confidence that I got the right thing. Now, there is a built-in function to get the standard error. So I'm gonna put a little extra line here just because I'm gonna show you. I think it's SE. I might be wrong. You know what? I'm winging it. Tell you what, let's not do it. So there is a function that will allow you to do just the, that will allow you to calculate the standard error. It might be like .ste or something like that. But what you can do also is we can use our formula here. So our formula up here is that the standard error, this whole quantity is the standard deviation divided by the square root of the sample size. So to get the standard error, we can take the standard deviation divided by, and then this SEM. Yes, yeah, thank you. Standard error, the mean. That's right. Thank you, then. Okay, so, and we can divide by this, the square root of the sample size. So the square root you have to either get with the math or the NumPy library. So I'm going to use NumPy because I already have it imported, and I'm going to say mp dot square root of the sample size. So my standard error is about 0.04. So just to make a point about, another point about the difference between the distribution of individuals and the distribution of the sample mean, we can think about and why the standard error is so much smaller than the standard deviation. If you think about, going out into the world, it would not be that unusual to run into somebody who was like, I don't know, 6'5", let's say, like tall, but not so insanely tall that it would just shock you if you saw them. I mean, we're not talking about like NBA player here. So if you went out and you found, you saw one individual that was like 6'4", 6'5", it's like, okay, yeah, they're tall, but like one person, that's not that big a deal. But think about, so in this situation, we have a sample of like 223 people. Think about if you went out and you got a sample of 223 people and the mean height was 6'4". That would be really weird. Like the only way that could happen is maybe if you were at the NBA playoffs or something like that, right? Having a mean height that was that bit high would be really weird. Again, because when you start having samples and you have sample means, tall people cancel out with short people, like extreme observations balance each other out. So we always expect means to be way less variable than individual observations. That's why it's so handy to work with means. That's why they work so well in hypothesis tests and stuff, is we expect the mean value to be way less variable than the standard deviation or than individual values. And so that's what we're seeing here, is that we expect just individuals walking around, their body temperatures could vary a fair amount. But if you go and you get a whole bunch of people and you take the mean body temperature, that, because individual high and low values will balance each other out, that mean we expect to be less variable. All right, so we've got the standard error here, and just for fun, I'm gonna do SE body temp with an extra underscore, and then we'll use that SEM function. So DF body temp dot SEM. Okay, And so we get exactly the same value because the SEM function is doing exactly the same thing as the, doing the exact same division that we're doing. I just wanted to point that out, that this function also exists. So we are at 3 out of 4 quantities that we need for our confidence interval, everything but the T star part. So we've got our sample mean, and that was about, let me look at my notes. That was about 98.17 degrees. Plus or minus T star times 0.53 was our standard deviation divided by the square root of our sample size, which was 223. And then if we actually calculate the standard error, which we did, we get 98.17 plus and minus T star times the standard error. So now it is time to understand what T star is doing in our equation. Okay, so what we're saying is when we calculate a confidence interval, we start at the sample mean and we add and subtract some number of standard errors from around the sample mean. Okay, so we start at the sample mean and we're going to add and subtract some number of standard errors on either side. So what T star is doing is this is the number that tells us how many standard errors to add and subtract to either side. So, okay, how many standard errors do we want to add and subtract on either side? Well, this is going to require us to go back and look at the central limit theorem again. So here's our central limit theorem picture. So what the central limit theorem tells us, and this is a slightly different rephrasing of what we talked about on Monday, is again, the wonderful thing about the normal distribution is that most samples that you could generate from a population will have a sample mean that's very close to the population mean. And few will have a sample mean far away from the population mean. Well, we can even actually go farther than that. We can say more precisely, what is a lot? What is most samples will have a sample mean close to the population mean? Well, we can actually say that we can expect about 95% of samples to be within about 2 standard errors of the population mean. So way back on Monday, we kind of quickly passed through a graphic that said, one of the reasons, so part of the reason that we care so much about the normal distribution is it has this really nice property where about 68% of observations fall between plus and minus 1 standard deviation. If you're talking about one observation, or plus and minus 1 standard error when we're talking about the mean, 95% of sample means will fall between plus and minus 2 standard errors, and 99.7% will fall between plus and minus 3 standard errors. So we're just rephrasing that. We're saying, okay, we know that 95% of samples ought to have a sample mean within plus and minus 2 standard errors of the population mean. So we are saying about 2, and I'm saying about 2 for a reason. And that reason is that exact number that's about 2 is going to depend a little bit on our sample size in the form of this quantity called the degrees of freedom. And again, I said degrees of freedom is one of those things that students really don't like because it's a hard concept to explain. They work different ways when we're talking about the in a different way when you talk about the chi-squared distribution and the t-distribution. And again, degrees of freedom are basically a general, they're a way to capture variability in a model. In the case of the t-distribution, the degrees of freedom is related directly to the sample size. So the degrees of freedom is the sample size minus 1. And so really what matters though in this case is that we're saying we're saying that 95% of the time, if we went out and we collected a sample, the sample mean is going to be between about 2 standard errors of the population mean. Well, we say about 2, well, exactly what it is, what that number is going to depend on how big a sample you're working with. All right, so the central limit theorem. So the idea, let's go back up to this picture and I'm going to show you, I'm going to skip ahead and I'm going to show you another picture too that I think is going to be more illuminating. So the idea is that, right, we said 95% of samples we expect to fall within plus and minus 2 standard errors of the population mean. So let's think about hypothetically on this, x-axis, what values I could get for my sample mean. Well, I could get a sample mean that's really close to the population mean. And if I add and subtract 2 standard errors from that, then I'm going to capture the true population mean in my confidence interval. If my sample mean is like down here, then if I add and subtract 2 standard errors around my sample mean, well, that's also going to capture the population mean. Or if I'm like up here and I add plus and minus 2 standard errors to this value of the sample mean, I'm still going to capture my population mean. It's only when I get outside of 2 standard errors from the population mean where I would not still capture the population mean in my interval if I added 2 standard errors. And so remember, we only take one sample. We don't know which sample we got. We don't know if we get a great sample mean that's really close to the population mean. We don't know if we have a dud that's way out here that's not going to, generate a confidence interval that captures the true population mean. We don't know that we have an almost dud that almost doesn't capture the true population mean. We don't know which one we've got. But by the central limit theorem, there's a 95% chance we've got a good one and a 5% chance that we've got a dud. Excuse me. So I want to show you one more picture before we go further, because I think this is a really good graphic. So again, what we're trying to do is we're trying to create a confidence interval that overlaps somewhere the true population mean. We only take one sample. We generate one sample mean. So on this picture, these little circles, those represent the sample mean of doing the experiment multiple times. So 20 times. And we see that if we did this experiment 20 times, then in all but one of them, no matter what the sample mean was, if we add and subtract 2 standard errors, it's that confidence interval still overlaps the population mean. There's only one chance. So we only have basically when we do our experiment, we have no idea which one of these lines we're generating with our confidence interval. But mathematically, we can say that, but mathematically, we can say 19 out of 20 times, our confidence interval is going to be just fine. It's somewhere going to overlap the population mean. only 1 in 20 times, and 95 out of only 1 in 20 times is it not going to. So we basically we like that chance, right? We're going to take a chance. We're going to go out, collect a sample, make a confidence interval, take a chance that it's going to capture the true population mean. But we expect that 95% of the time we're going to capture the true population mean. It's sort of like if somebody said, you can play the lottery and you've got a 95% chance of winning. I mean, there's a 5% chance you're not going to win, but geez, you got a 95% chance you're going to win. That's a pretty good chance. You can, I would certainly want to go with it. And so it's that about 2 value of T star that's going to allow us to have that 95% chance that we are going to capture the true population mean. Okay, so I want to pause and give everybody a break. What questions do you have before we break?
I've got one. So
yes.
The standard error is analogous to the standard deviation. It's just in this case, we're talking about in reference to the mean.
Yes.
All right.
That's exactly right. Yeah. Anybody else? Okay. So we'll break here and then we'll talk about how to actually calculate T star, and then we'll talk about the easy way to do all of this. Well, the easy-ish way. Okay. So we are back and we are poised on the edge of calculating our confidence interval. We said we are going to want, we said because of the central limit theorem and knowing that we expect 95% of sample means that we could calculate to be within plus and minus 2 standard errors of the population mean, that we could rephrase that as saying we're 95% confident that the true population mean falls within about plus and minus 2 standard errors of the sample mean. So again, we're still at that about part. We've got to actually come up with an exact value, and that's going to be based also on our sample size. So what we are wanting here is we are wanting a value that is a number of standard errors above or below the population mean, such that 95% of our data is trapped within plus or minus that value. So there is a function in the t distribution called tppf that returns a value, that returns that value for you. So it returns this number that is plus and minus 2 standard errors above and below, plus and minus 2 standard errors above and below the sample mean, depending on what that needs, or for what it needs to be depending on your sample size. But to get that number, so what it returns is it returns this number, that plus and minus something close to 2. It returns it when you feed into it the proportion of data that you expect to fall to the left of this line. So because we expect 95% of the data, the middle 95, to fall to the left of the line, plus half of the remaining 5%, the number that we have to put in here in the front of this tppf function is 0.975. So again, and we're going to make this a little bit easier in a minute. I just want us to get a value of t star out so we can look at t star on its own real quick. So the reason this says 0.975 for a 95% confidence interval is because we've got to get this value here such that the middle 95% of our data is to the left of that number, plus half of the 5% that's left over. So that's where that 0.975 comes from. And this is going to be made easier shortly. So we need to say we want 0.975 to the left of that value. And then we also said that exactly what this value of t star is going to depend on our sample size. So we need to give it our sample size in the form of degrees of freedom. So our sample size, we used n body temp, that's our sample size. So our sample size, or our degrees of freedom, is body temp minus 1. So we can run this. And we see what we get for our value of t star is a number that is very close to 2. So that's what we expected. We expected it to be very close to 2. 1.97 is very close to 2. It's 3/100ths shy of 2. And remember, we said we expect this thing to generate a number that's very close to 2. We're going to want to add and subtract about 2 standard errors from our sample mean. So exactly what this number is depends on the number of degrees of freedom. It depends on the sample size. But again, just wanting to point out that our value of T star here is a number that's really close to 2. So coming back to our formula, we got all these pieces that we already calculated earlier. The one thing that we need to add in is T star. So we're going to have our 95% confidence interval. So we expect this to work for 95% of samples that we could generate, or that generated from our data, or that we could have gotten collected. We expect, so we're 95% confident that the population mean is captured between 98.17 plus and minus this number that's very close to 2 times the standard error. So within just about 2 standard errors of our sample mean. And so remember, we said that this quantity, this T star times our standard error, is called the margin of error. So if we wanted to just calculate the margin of error, that would be 0.07. So if you were writing about this in a newspaper article, it would say we have found that, or we estimate that in 1997, the true healthy human body temperature, the mean healthy human body temperature is 98.2 degrees, asterisk, and then at the bottom it would say asterisk plus or minus 0.07 degrees. All right, so we can use these numbers. So the plus and minus just means we're going to take 98.17 and subtract off this quantity. And then to get the upper end of the confidence level, we're going to take 98.17 plus 0.07. So we can use we can use Python, basically like a calculator in this case. And we can say the lower confidence limit is equal to 98 point. Well, actually, what I want to do is I'm going to use all my things, my variables that I assign things to. So I'm going to take the mean body temperature and I'm going to subtract off T star times the standard error. And to get the upper end of the confidence limit, I'm going to add. All right, so my lower end of my confidence interval is 97.12 and my upper end is 97 or 99.2. So in conclusion, and confidence intervals have a very kind of prescribed way of explaining what your conclusions are. So we start by saying what level of confidence we're using, because we're going to look at how to do different levels of confidence just in a minute here. So we can say we're 95% confident. So this has to do with that adding and subtracting about 2, because we expect about 95% of samples, we expect 95% of samples that we could have drawn to be within about 2 standard errors of the population mean. So we're 95% confident that the population mean healthy human body temperature. So the other thing about confidence intervals is we always want to make a statement about the population parameter, the population mean. We've got the sample mean. We can work with this. We were working with the sample mean. So we don't want to make a statement about the sample mean. We want to make a statement about the population mean. So we're 95% confident that the population mean healthy human body temperature is between about 97.13 and 99.2 degrees Fahrenheit. So again, coming down here and looking at this picture one more time to talk, just to reiterate, what does 99.5% confident means? It means I went out and I got a sample and I calculated a sample mean and I calculated this confidence interval. And I don't know if it was one that's almost overlapping the population mean. I don't know if it's one that's almost exactly lines up with the population mean. I don't know which one of them it is. But I'm pretty sure, I'm 95% confident that I got one of these good ones. I only think there's a 5% chance I got a dud. So I don't know absolutely 100% for sure that the true population mean healthy human body temperature is within this range, but I'm pretty darn sure it is. Like there's a 5% chance that that it's not between these two numbers, but I have a pretty high level of confidence, 95% confidence that it is. I think this is with a high degree of certainty. I think that's a good estimate of the true population mean. Okay. So questions.
Might it be a good idea to say in conclusion, based on the data, because we probably didn't go out and collect it. We're just analyzing it. I mean, as maybe like a liability disclaimer.
Well, sure. Yeah. Yeah. Based on the sample that we collected, this is what our estimate is. And so, it actually raises a good point that probably was made somewhere in this paper, which is that, there perhaps are limitations to the conclusions. I mean, we don't have any idea, at least I don't have any idea, how representative the people in this sample were of the American populace broadly or the world broadly. I mean, there could be any number of ways where they perhaps weren't exactly representative of the entire population. That's just the kind of the way that it works. But yes, so it's sort of like as best as we can guess from our sample, hoping that it is representative, it's representative of our population. This is our best guess that we have to go on. And if we know, as scientists or, data analysts, there is some way in which our sample is not representative of the population, then we have to acknowledge that. So one thing that came up a lot of times when I was working in the ophthalmology group is that there's a lot of eye diseases that affect different ethnic groups differently. So diabetic retinopathy affects the Hispanic people of Hispanic and Mexican backgrounds differently than it does other groups. African Americans can have different risk factors. We were in South Central Wisconsin. There are not a lot of individuals of African Americans or people with Latinx backgrounds in South Central Wisconsin. So we had to say our results are quite limited. We can't generalize to other populations. And that wasn't because, that was just that it was a location issue, basically. That's where we happened to be. And, these studies were started back in the 70s and stuff. But so it is important, if you're ever working through data and you have some sort of limitation and your data is not generalizable, it's important to acknowledge it. Yeah, it is important to put those kind of caveats. They are important context for anybody who's reading your results. So Eric asked, for the confidence limit, we're using the standard deviation instead of the SCM. Oh, thank you. No, it should not be the standard deviation. You're right. It should be the standard error. Thank you for pointing that out. That was a typo on my part. Okay. Thank you, Eric, for pointing that out. No, this should be the standard error. So we're saying it should be between 98 point about 1 and 98 point about 2 degrees Fahrenheit. So notice here again, when we're talking about the standard error as opposed to the standard deviation. So we're talking about how variable means are as opposed to how variable individual observations are. We have a really, really pretty precise estimate about what the true mean healthy human body temperature is. And again, part of that's because humans can't exist in a very wide range of temperatures. Okay, so we can do this a slightly easier way. Using, but not that much. It's gonna make the T-star issue go away. Oh, Kyle, I'm gonna ask you a question in just a second. Oh, you have a very good question, Kyle. Would the probability of getting a bad confidence limit go up as we repeat the calculation? Let me talk about that later. That's a very good question. It raises is a very important point. Because actually it's the opposite. The probability, well, yes, actually, okay. So yes, the probability that you would get a confidence limit that doesn't, yes, there's one of those, 1 out of 5, 1 out of 20 that doesn't capture the population mean, yeah, that goes up the more that you do. So we will talk about that in more detail later, but yes, that's a good question. Okay, so let's get rid of this whole T-star thing and make our lives marginally easier. So there is a function called T-interval that calculates the confidence interval for a T statistic. In this case, we can tell it what confidence limit we want, or what confidence level we want. So we'll start out by saying we want a 95% confidence level. Now, it's frustrating because they're calling this the confidence level alpha. And remember, we said that we talk about the significance level, we call that alpha. Well, those are two different alphas, and why they decided to call this parameter alpha in this function, I have no idea. I don't think it makes a lot of sense, but that's what they decided to call it. It would be better if they called it Fred the Panda, but they don't. It's called alpha. It's different than the significance level. We'll see that they're somewhat related, but it's a different thing. So this first thing is our confidence level. The second thing that we need is our degrees of freedom. So in body temp -1. And then we need to give it two more parameters. So we need to give it the confidence level that we want, the number of degrees of freedom, and then we need to tell it, it wants to know, it calls it the location, the location parameter. It says, hey, what do you want me to use for the center of this confidence interval? Well, I want, Python, I want you to use the mean body temp from my sample as the center of my confidence interval. And then it says, what do you want me to use as the standard error, the scale? How far do you want me to go, away from the mean? And I say, Python, I want you to use the standard error as the scale parameter. So center is going to be the mean, scale is going to be the standard error. So basically, this is all the stuff minus T-star. This is all the stuff that we needed to calculate the confidence interval by hand earlier. So if we run this, we get our confidence interval, both ends of the confidence interval. And if we go up, if we scroll up and look between the two, we can see we get exactly the same answer either way. So using T-interval does spare you a little bit of calculation. It's much easier to change the confidence level, and we're going to see what happens when we do that in a minute. But all this, the same calculations that you need to get this the confidence interval this way, sort of by hand, plugging everything in, is the same stuff that you need to use the T-interval function. So you need the confidence level, that's different, but you still need the sample size and the mean and the standard error. So one question is like, okay, well, what if I choose to be a different percent confident? Well, you can do that because T-star is just a number, and that is the number that controls the level of confidence. We said about 2, that corresponds to 95% confidence. But if we wanted to be more confident, we would have to go out plus and minus more standard errors. And so we would have a bigger value of T star. If we were willing to be less confident, we could go out less standard errors, plus and minus fewer standard errors, and our T star would be a smaller number. So it's a little bit hard to see here because we are dealing with pretty similar numbers, but if we rerun our confidence interval statements here, so we can change this and we can make a 90% confidence interval, and then we can look at a 95% confidence interval, which we just did before. And then we can look at a 99% confidence interval. Now, I will say 95% confidence is by far and away the most common value that people use for confidence, for a confidence interval. This is completely arbitrary. If you want to blame anyone, oh, I guess I didn't paste this guy in there. If you want to blame anybody for confidence intervals, if you don't like them, you can blame them on a guy named Jersey Naaman, who was kind of, I think he was kind of a jerk also. I'm not totally sure, but he is a guy, he is very much involved. He was working with R.A. Fisher and another guy named Egon Pearson. Egon, just like from Ghostbusters, who also had a famous statistician father named Carl Pearson, who actually I should put him in there real quick too. So that's Jersey Naaman. He was really, again, involved in confidence intervals. And then Carl Pearson, should have brought him up yesterday. He was kind of an awful human being also, I'll be honest. But he was really involved in all the chi-square stuff that we did yesterday and contingency tables. So you may run across those names also. And again, yeah, he was a really famous statistician. He did a lot of, if you've ever heard of the journal, scientific journal Biometrica, he was like really obsessed with measuring people, and it was like a gross eugenics kind of thing. But actually, like, yeah, he did a lot of early work in biostatistics kind of stuff. And a lot of it is icky. But anyway, those are two guys, two famous statisticians' names worth knowing, linked to the stuff that we're doing. Okay, so back to confidence intervals. All right, so we can look very closely, very, very closely, like with our magnifying glasses, at sort of the hundredths place of these three confidence intervals. So, sorry. Okay, so if you look at them very closely, what we want to compare is the width of the confidence interval. And by width, I mean the difference between the biggest number and the smallest number. So if I took 98.223 and I subtracted off 98.11, and I did the same thing here, and I did the same thing here, what I want to observe is which of these three confidence intervals, 90, 95, or 99, is the quote widest. So which one is going to have the biggest, I guess the biggest range, if I take the biggest number and subtract off the smallest number? Which one is going to give me the largest range or the largest width? Very good. Yeah, and the 99% confidence interval. That one is going to give us the widest range. And hopefully that makes some intuitive sense, right? If I want to be more confident that I guessed the right number, well, I ought to guess a wider range of numbers. If I'm willing to be less confident that I got the right, exactly the right number, well, I could guess a smaller range of numbers, a more precise range of numbers. So, okay, so we're talking about this. So I want to be 100% confident, like, right? I mean, we want to be right here, people, you know, this is why we're in data science. We like numbers. We like to be right. So, but But what happens, but what if we want to be 100% confident? Well, this is playing into this trade-off that we're going to have between accuracy and precision. So accuracy and precision sometimes, and I don't think I have my good picture that I like here. Okay, so let me look at this. All right, so we've got two concepts going on here. Okay, so let's look at this picture maybe. Okay, yeah, so here's a good picture here. And I'll try to copy this and put it in the, I almost said in the show notes. I guess I listened to too many podcasts, in the thread. Okay, so we've got two concepts, accuracy and precision. Accurate means I got the right answer. Precise means I have a very small range in my estimate. So looking at these pictures, here, our results are accurate and precise. I hit the bullseye, I got the right answer, and also my estimate is, my shots at the target are very close together. Here, my shots are very close together, but it's at the wrong place, right? Here, I'm basically in the wrong place, but my range is all spread out all over the place. And then here, I'm not accurate or precise. That means I'm all over the place and I'm in the wrong place too. So we want accurate and precise. Unfortunately, because we don't know exactly what the bullseye is, we have a trade-off between being accurate and precise here. So the more accurate you want to be, so meaning the more likely you want to be to capture the true population mean in your confidence interval, the less precise your confidence interval will be. So basically, the wider the range your confidence interval will be. Okay, so we just saw that a 95% confidence there. Sorry, the 99% confidence interval was the widest one. If I want to be more confident that I've got the right answer in my range, well, I'm going to make a bigger range. On the other hand, the less accurate you're willing to be, the more precise your estimate can be. Leading up to the point that at the point that you were 100% confident with your confidence interval, it would probably be so wide, it would be completely meaningless. So, in terms of baking brownies, well, I'm 90% confident that the brownies are going to be done in 35 to 36 minutes. So that's a pretty narrow range of a guess of how long they're going to be done. I could be a little bit more sure that they're going to be done somewhere between 34 and 37 minutes. And I could be a little bit more sure that they're going to be done between 33 and 39 minutes. And I'm totally sure they'll be done somewhere between 0 and 60 minutes. But 0 and 60 minutes is such a wide range that is totally meaningless. Like, yeah, it's true. It's completely accurate. They're going to be done somewhere in there. But it's such a wide range. Again, like, that's totally unhelpful. So I need to balance that out. Like, I want to be pretty darn sure that I'm right, but I have to have like a confidence interval that I can actually work with, that actually like means something to me, that it's actually a meaningful estimate. And so, throughout the ages, I suppose, at least since the early 1900s, we've just kind of settled on 95% confidence interval being like a decent place to land, with 90 and 99% as sort of like backups. That's like second, the gold medal and the silver medal there, or I'm sorry, the silver medal and the bronze medal there. So questions. All right, so let's talk about some common errors interpreting confidence intervals. So a correct statement, summarizing our results, are that we're 95% confident. So there's my statement of confidence, how confident I am, that the population mean healthy human body temperature. So my second thing that I have is a statement about the population parameter is between 98.1 and 98.2-ish degrees Fahrenheit. So I've got my confidence statement, my statement about the population parameter, and my range that I calculated for my confidence interval. So what's wrong with this statement? We're 95% confident that the sample mean healthy human body temperature is in that range. So what am I saying wrong in that situation? So what is wrong about saying we're 95% confident that the sample mean body temperature is between those two values? It's not, I guess I should say it's not wrong. It's not incorrect. It's just not the correct way to talk about a confidence interval. Exactly. Thank you, Eric. Perfect. We know, yeah, we don't want to make a statement about the sample mean. We know what the sample mean is. We calculated it. That's not what's interesting. We want to make a statement about the population mean. So we don't want to make a statement about the sample mean. We want to make a statement about the population mean. Okay, so next, we're 95% confident that the sample mean healthy human body temperature is 98.17 degrees. Yeah, so Andrew says we're using population mean and sample mean as being interchangeable when they aren't equal. Exactly right. Those are two different things. So we want to make sure we're talking about the right thing. Okay, so here's our second incorrect statement. We're 95% confident that the sample mean healthy human body temperature is 98.17 degrees. So what are we not doing correctly there? Yes, exactly. So CJ says we are not providing a range. Right? We don't think, yeah, and Andrew said the same thing. So in that case, we're thinking that the population mean is probably exactly equal to the sample mean. Well, we don't think it's probably exactly equal to the sample mean. We just think that it's within a range of the sample mean. So that's our incorrect statement. So this last one is the trickiest one. 95% of samples will have a mean that's between 98.1 and 98.2 degrees Fahrenheit. What's wrong with that one? And I think looking at this picture is the most is helpful for thinking about why that's not correct. Think about the endpoints for all of these graphs, those confidence intervals. Okay, so this is, okay. Percent of samples doesn't equal the confidence level. So what it is that we expect 95, and this is the subtle one, this is the tricky one. We expect 95% of samples to have a sample mean that contains the true population mean. However, we don't expect all the endpoints to be exactly the same as we got with this one sample. Okay, so looking at the picture, and again, this is the subtle one, this is the tricky one. We look at what we see is we expect 95% of confidence intervals. So here, 19 out of 20 confidence intervals to overlap the true population mean, but we don't expect their endpoints to be exactly the same. So we don't expect 95% of samples to have exactly this set of endpoints. We just expect 98% of samples to contain the true population mean, but they could be shifted in all kinds of different directions. Okay, so questions. I think after this, we're in a little bit of a grab bag of different topics. All right, so I'm gonna give us another break here. And when we come back, we'll kind of do a grab bag here. All right. So here's our last little bit here. Let's get rid of accuracy and precision.
Hey, Chelsea, I got a question.
Oh yeah, please.
Okay. Yeah, I'm a little bit slow on the uptake sometimes.
No.
And well, Kyle had said, would the probability of getting bad confidence limit go up as we repeat the calculation? I know you said that you were going to touch on that, but then looking at that graphic, I had 5 minutes to think about it.
Mm-hmm.
Could we run this same set of data 20 times? And so we get our accuracy, I guess, right?
Mm-hmm.
And then we run the results of all 20 times and then look for the outlier, exclude that, and then run it one last time and get our precision. Does it work like that?
So the issue is that when we're doing this, we're thinking about our population typically being difficult to get a sample of. So if we're thinking about human beings or something like that, we really have one shot at our sample. We don't know what that sample mean is. What I sort of meant when I was talking about Kyle's comment is that the more times you make a confidence interval, the more, for like in different scenarios, the more likely that it is that you're going to have get a confidence interval that does not contain the population mean. So let me keep going a little bit to try to elaborate on what I mean, because we're going to get there in just a second. But those are good questions. So I guess the answer to your question is, because if you're working in a lab or something and it's really easy to replicate your experiment or replicate the sample, that might be an approach that could work. But typically when we're doing any data collection thing, it's really expensive in terms of time and potentially money to get a sample. So it's like, that's our sample. It's difficult to like replicate that sample 20 times and say, okay, which is the one that's weird. Okay, so first thing real quick first is degrees of freedom. So again, I said degrees of freedom is a way of capturing uncertainty in the model. They work a little bit differently in the two things we've talked about, t-tests and chi-square tests. And it's going to work, yeah, a little bit differently next week in regression. I personally don't think it's super important to know exactly what degrees of freedom are in every case, beyond the notion that they capture uncertainty in the model. But this is a link to a good article if you want to look in more detail, sort of mathematically what degrees of freedom are. So second thing, and this is one of the kind of, so second thing is the correspondence between confidence intervals and hypothesis tests. So it's not a coincidence that we have 95% confidence and a 5% significance level when we're talking about hypothesis tests and confidence intervals. Like those are kind of like, sides of a very unbalanced coin, I guess you could say. But so what we can actually do, so with one caveat, and it's a caveat and a problem we're never going to run into at Lambda School, but you can technically, and this is not, it's not generally done, but just know that it's out there, and sometimes people will do this, but this does not work if you don't have a not equal to alternative hypothesis. So it is possible to set up a hypothesis test with a greater than or a less than alternative. It's not great practice, but sometimes people do it. In that case, if you have the greater than or not or less than alternative hypothesis, this whole thing I'm about to talk about, it does not work. But we're not dealing with any of those situations, and you probably won't ever deal with one of those situations. You'll probably always have a not equal to alternative hypothesis. So when you have a not equal to alternative hypothesis, you can actually get these, you can actually determine if you should reject or fail to reject that hypothesis based only on looking at a confidence interval. So let's again think about what the confidence interval is telling us. We're saying we're 95% confident that the true population mean is in that confidence interval. So let's, thinking about the temperature example, my null hypothesis was that the mean human body temperature is 98.6 degrees. So I want to evaluate, is 98.6 degrees, is that a good guess about the normal human body temperature or a bad guess? If it's a good guess, I'm going to fail to reject the null hypothesis. If it's a bad guess, I'm going to reject the null hypothesis. So my confidence interval gives me my range of good guesses. So if my null hypothesis value is in my confidence interval, I think it's a good guess, and I fail to reject the null hypothesis. If my null hypothesis value is not in my confidence interval, I think it's a bad guess, and I am going to reject the null hypothesis. So if it's a 95% confidence interval, I can reject at the 0.05 level. If it's a 99% confidence interval, I could reject my null hypothesis at the 0.01 level. If it was a 90% confidence interval, I could reject at the 0.1 level. So like here, thinking about the human body temperature example, I am 95% confident that the population mean healthy human body temperature is within 98.1 and 98.2 degrees Fahrenheit. That's my range of what I think is a good guess about mean healthy human body temperature. 98.6 degrees is not in that interval. So that was my old null hypothesis value. So I take my null hypothesis value, 98.6 degrees, I say, is it in the confidence interval? It's not. That makes me think, oh, that's probably not a very good guess about the true population mean, because it's not in my range of good guesses about the population mean. So I'm going to reject the null hypothesis. Again, I don't actually have to take the step of calculating the p-value or the t-statistic. I can just say, hey, is my null hypothesis value, is it in the confidence interval? Yep. Well, then I think it's a good guess. Fail to reject the null hypothesis. Is it in my confidence? Is it not in my confidence interval? Well, that's a bad guess. I am going to reject the null hypothesis. So often, when people are presenting results, they'll just present a confidence interval, and then they'll say, okay, this is our hypothesis, we reject or we fail to reject the null hypothesis, but they won't necessarily present like their t-statistic and their p-value. They'll just say, hey, here's my null hypothesis value. Okay, here's my confidence interval. Yes, I see my null hypothesis values in that. I'm going to fail to reject the null hypothesis. Oh, no, I don't see my null hypothesis value in there. Okay, I reject the null hypothesis. Okay, so a couple other things. Okay, so we're almost done. All right, so one other thing that we need to keep in mind, again, this comes back to the pizza theorem, I don't know, where we were talking about increasing the sample size. So we're increasing the denominator, increasing the number of slices of pizza, and therefore decreasing our standard error. What would happen? We can ask ourselves the question, we can look at what would happen if we increased our sample size from 223 to 500, but everything else stayed the same. So two things would happen here. So we're changing our sample size from 223 to 500. So we're going to have 499 degrees of freedom. So our sample size is increased to 500. We're going to have to run all this stuff together, and we can calculate the margin of error here, because the sample mean is not going to change. It'll just be the margin of error that would change. So if we run the margin, calculate the margin of error, what did I do wrong? I just named this something different. Hold on. Oh, okay, underscores. Sorry, lots of underscores that I didn't have before. Oh, I get change mean too. Oops. All right. Sorry, guys. Okay, so now I've got a new margin of error. So my old margin of error was about 0.07. If everything stayed exactly the same, but I increase my sample size, I get a smaller margin of error. So this is basically, so we just talked about how when you choose your confidence level, you have a trade-off between accuracy and precision. So if you want to be really accurate, you're going to have to get a wider confidence interval. And if you want to be really precise, well, you're going to have to give up some confidence. Well, the only way you can sort of have your cake and eat it too is by getting a larger sample size. So the larger the sample size that you have, the more accurate, or if you're able to increase your sample size, you are able to become more accurate and precise. That's the only way that it works, is a larger sample size allows you to be more accurate and precise for the same level of confidence. All right, so that's a good thing. So here's the bad thing. Here's the thing, a thing that we need to talk about, which is that throughout this whole thing, we've been talking about 0.05 significance level and 95% confidence. And, baked into this whole thing is we're saying, it's most likely that we're going to get a good sample with a good sample mean just by chance, but there is a chance that we will not do that. We're going to be, our sample is going to be this guy that doesn't overlap the population mean, again, just by chance. So we would like to quantify the likelihood of us making these mistakes. And so when we actually do a hypothesis test, there's 4 different things that can happen. There's 4 outcomes that are possible. So the first one, so let's do the easy ones first. So just as an example, okay, so what we're going to do is we're going to pretend that, well, not pretend, but so out there is some truth about what's really going on, that either the null hypothesis is correct or the alternative hypothesis is correct. So either healthy humans have a mean body temperature of 98.6 degrees, or it's not that. Now, we, with our weak and puny human minds, we don't actually know the actual truth. Perhaps highly intelligent aliens somewhere know which is actually really true for every single human being on this entire planet, but we don't know that. All we can do is we can go out and get our sample, and we can make a decision based on our hypothesis test. So if the null hypothesis is really true, if humans really have a mean healthy human body temperature of 98.6 degrees, and we fail to reject the null hypothesis, we conclude that the healthy human body temperature is 98.6 degrees, then we have done the correct thing. So this is correct. If the null hypothesis is really true and we don't reject it, well, that's good. On the other hand, if the alternative hypothesis is really true, healthy human body temperature is not 98.6 degrees, and we reject the null hypothesis, well, we have also done the correct thing. Be happy. But there's two things that could happen that are not happy. So the first thing that we could do is the null hypothesis is actually true, but our data leads us to reject it anyway. We call that a type 1 error. Right? The mean healthy human body temperature really is 98.6 degrees, but we got a crazy sample just by chance. We rejected the null hypothesis. We've made a type 1 error. The other thing that we could do is the alternative is true. The healthy human body temperature really isn't 98.6 degrees, but we failed to reject the null hypothesis. Excuse me. And when that happens, we call that a type 2 error. So in words, a type 1 error occurs when you reject the null hypothesis, but it really is actually correct. And it's actually easy to figure out the probability or the chance of making a type 1 error. It's equal to the significance level. So if we have a 0.05 significance level, there's a 0.05, there's a 5% chance that we're going to make a type 1 error. A type 2 error occurs when we fail to reject the null hypothesis, but the alternative is really true. And so figuring out the probability of a type 2 error is really quite tricky, and it involves a lot of assumptions. So we're not going to worry about actually calculating a type 2 error. Except to say, so what's really important with type 2 errors is how it relates to a concept called power. So type 2 error is is failing to reject the null hypothesis when you should. Power is the ability to reject the null hypothesis when you should. So if we suspect we are making a type 2 error, we often say we are underpowered to reject the null hypothesis. Statistical power is the ability to reject the null hypothesis when it is false. Why am I writing the set code itself? I have no idea. Oh, I see what I did. Okay, so statistical power is the ability to reject the null hypothesis when it's false. So power is one of those things that we want a lot of. Like we want a big sample size. Big sample size is always great. Having a powerful test is always great, right? We want to be able to reject the null hypothesis when we should. That's a good thing. So we want a powerful test. And having a powerful test means that we have low type 2 error. Again, calculating power and type 2 error are tricky and involve a lot of simplifying assumptions. So we're not going to, if you ever had to do that on the job, they would say, this is how we calculate power, calculate the power like this. Because it's again, it involves a lot of simplifying. It involves a lot of assumptions. It's kind of voodoo. But what's important to know is there are three main things that influence statistical power. So the first is sample size. So we want more power. Bigger sample size is always related to better things. So if we have a larger sample size, we end up with more statistical power. We end up with a more powerful test. Another thing that is trickier to understand is that a larger significance or alpha level, so I'm using those words synonymously. The larger the significance level, the larger the more power that you have. And so this can seem kind of tricky. So let me see. Okay, so if I want to compare a p-value, a significance level of 0.05 and 0.01. And my p-value is 0.02. So if I have a p-value of 0.02, I'm going to be able to reject the null hypothesis at the 0.05 level, but not at the 0.01 level. So the more power being able to, power is the ability to reject the null hypothesis. So if I can reject the null hypothesis at this significance level, but not this significance level, this is the more powerful test, the one with the larger significance level. Now, notice perhaps the problem here. So this means that the more powerful test, so remember the significance level tells us the type 1 error. The bigger the significance level, the more powerful the test, but the more likely you are to make a type 1 error. So the more powerful the test, the more likely you are to make a type 1 error. So another one of these things where, we have an interplay of how big do I want my significance level to be? How much do I not want to make how powerful do I might want to make my test? Well, I could make it more powerful by changing my significance level, but that would also have the effect of causing me to potentially be more likely to make a type 1 error. And the last way that we can make our tests more powerful is by increasing what we call the effect size. So the larger the effect size, the more power our test has. So when the sample mean is really similar to the population mean, it could be very hard to detect a statistically significant difference between them. On the other hand, if the sample mean is really different from the population mean, if the sample mean is really similar to the mean under the null hypothesis, it can be very hard to detect a statistically significant difference between them. However, the sample mean is really different from the mean under the null hypothesis. SIS. It's going to be a lot easier to detect a statistically significant difference between them. So the bigger the difference between what you propose under the null hypothesis and what you actually see in your sample, the more power your test is going to have. And power and error are tricky, but it's worth knowing. I think it's just worth being aware of the potential, I don't know, mistakes is not the right word for it, but I think it's worth knowing about this idea that your tests can be underpowered to detect a statistically significant difference. So if you fail to reject the null hypothesis, you can consider the fact or consider the idea that your test, that it wasn't really that there's not a difference, it's just simply that you don't have enough power. Now, so that's, again, related to type 2 error and power. Now, this p-hacking thing that I'm going to talk about here in just a second, and that was related to what Kyle was talking about earlier, this relates more to type 1 error. So p-hacking, I said, AKA, is the problem of multiple comparisons. So what p-hacking is, so related to the p-value, so p-hacking is the practice of doing a bunch of hypothesis tests or creating a bunch of confidence intervals until you find one that is statistically significant. Because again, because the problem is, just by chance, we expect to reject the null hypothesis incorrectly about 5% of the time. So for example, if you were really motivated to find a statistically significant result, if you did 100 hypothesis tests, you could expect 5 of them to be statistically significant just by chance. Or if you did 20, you would expect 1 to be significant just by chance. So, again, yeah, the more hypothesis tests that you do, let's say you have a data set that has like a zillion columns in it, well, you could do a zillion t-tests, or you could do a zillion chi-square tests, or you could make a zillion confidence intervals. And you'll probably find something that has a statistically significant result, but again, just by chance. Or you won't know if what you did was just by chance or if that was a real result. And so this is why we talk about, you always want to lay out your hypotheses before you start working. It's okay to have more than one hypothesis test you want to run, but you have to lay out everything beforehand. And there are also ways to account for making multiple, wanting to make multiple comparisons. And one example is this Bonferroni correction. There are also 2 similar corrections that were created by 2 other statisticians, John Tukey and somebody Chaffee. I can only ever remember his last name, Chaffee. They all basically work the same way. So I do, and I know we're headed into lunchtime. I'll give you the data give you this example later. But I just wanted to point out one other interesting figure that illustrates what to do. So this idea of wanting to make multiple comparisons, this is a fine thing to want to do. It's not good to p-hack, but you perhaps maybe one day might want to make a lot of comparisons. And one time when this is done very commonly is dealing with genetic data. So in a lot of genetic studies, they look at, genes, or perhaps even at the base pair level. So we call them single nucleotide polymorphisms, or SNPs, but they want to look at every single base pair, more or less, on all of the DNA, on all of the, for a whole person. This is like millions and millions and millions of things to see if any of them are associated with the presence or absence of disease. So basically, we're talking about doing perhaps million chi-square tests, or at least thousands of chi-square tests. That's what we're doing all at the same time. So the likelihood of having lots of type 1 errors is very high, right? We're doing so many tests, we're going to make a lot of type 1 errors. And so what has to happen is, mathematically, they have to say, well, we can't say for any individual test, we can't look for significance at the 0.05 level. We have to look at like the 0.00001 level or something. So don't worry too much about this negative log 10 thing, but basically what it is this is saying like how many zeros there have to be before the 1 for a result to be statistically significant. Does it have to be smaller than 0.0005, 0.00001? Sorry, I need my fingers for this. Or like 9 zeros and a 1, or 14 zeros and then a 1. And what we see is that in cases, so, we've got a lot, we're going to end up with lots and lots and lots of significant p-values at the 0.05 level. But here we get these skyscrapers, that's why this is called a Manhattan plot, that are so significant, even at the, 1 times 10 to the minus, 16 or 18 level. And then we can say, out of all of these comparisons that we're doing, this guy, like that one's the one we're really interested in, or whatever's going on this gene. So we see a lot of hits right at the same spot. This gene, this allele is interesting. So just a cool figure illustrating it. So like, we talk about don't do p-hacking yet. You may want to make multiple comparisons one day, and there are ways to work with that. All right, so questions about confidence intervals. Okay, I don't want to keep you any longer. I will let you eat lunch. I will send you the code that works through one more example too, just in case you want to see another confidence interval example worked through. Otherwise, have a good afternoon, and I will see you around.